I just like am bad at layups. It's really weird.
Wow. How is everybody? Alive.
How did your trusses happen?
My trusses did not happen, sadly. Our prayer that the rain would hold off was answered, and the framing crew never showed up with the crane. They didn't tell us. We tried to call and everything. Something fun came up. He wanted to go. The foreman wanted to go do something fun, and instead it left us trussless, and it was. We already did. So, yep, sadly. But I did bump into a calculus problem that has to do with my addition. So yeah, I'll tell you guys about it in a few minutes. So, anyone get engaged over the weekend? Anyone get a mission call? We got anyone that's got a mission call yet this semester? Where to? Paraguay. Oh, awesome. Great. Anyone else? All right. Anyone got back from a mission this semester? And like, kind of a weird question because, you know, if you got back during it, you probably weren't registered for class. But, you know, if you got back within the first week, every once in a while I'll have a student that gets back the first week of class and still gets in. Okay, let's get started. Is it time? Seems like it is. Who'd like to start us off with a prayer? Thanks. Wait, you've already said it. Someone that hasn't said it for us yet. All the brave ones have said it. Thanks, Austin. Amen. Thank you so much. All right. So quickly, I'll tell you about the calculus problem that showed up. I'll just write down at the bottom here. So we're getting some basement stairs poured. We have an external entrance to the basement that we're putting in, and the guy that's going to be doing the cement, he actually is a calculus teacher in high school, but he also does concrete on the side. Make ends meet as a teacher. But he came to lay out the stairs, and he drew this line. This is my fill line, and that's how much you have to have rock up to before he pours the concrete to fill in the stairs. But I currently have some rock there already, which is right there. Oops, that's kind of bad. So I currently already have rock to there, and I have to estimate how much more rock that I need. And so I needed to calculate the area between these lines and multiply it by the width of the stairwell to get the estimate of how much stuff there is. And you guys know how to find the area between two lines like that. So I actually didn't use the calculus. I did geometry to just figure out the area of the triangle, since it was simple enough. But still, I just thought it was funny that I bumped into a calculus problem. Okay, let's talk a little bit about partial fraction decomposition. If you need to go, if you want to take a picture of these, do it really fast, and I'll still give you some time to work on the problems. But I'm going to move on, and then we'll come back. Okay. If we have something like this problem where we're adding these together, it's supposed to be a 2. You learned how to do this many years ago in algebra. You get a common denominator. We can do it here by just multiplying those two together. And then I have to multiply my 3x times x minus 1 and my 2 times x squared plus 1. And then I can distribute those out, and I get a 3x squared minus 3x plus 2x squared plus 2. And I can also multiply these out down here, and I get an x cubed minus x squared plus x minus 1. I can simplify that numerator. I've got 2x squareds there, so I get 5x squared minus 3x plus 2 over x cubed minus x squared plus x minus 1. All right, so you guys have learned how to go forward this way. Go from there to there. It's pretty straightforward. Partial fraction decomposition lets us go back, because it's kind of crazy to try to integrate that thing. Okay, but if we can break it up into the sum and difference of some simpler rational functions, then maybe we can actually find antiderivatives of those. So, but it's a lot harder to figure out what they came from, especially trying to figure out what here is in the numerator, what those coefficients are, than just going forward. So that's the general idea of partial fraction decomposition, is we're going to get things that are in this form. We're going to have a rational function, and we're going to try to break it up. So, okay, let's go back and, oops. There, take 10 more seconds on this. I'm going to close. All right, so we'll do this problem. We'll talk about more complicated setups in a minute, but let's just do this problem. I'm going to multiply both sides by x plus 1, x minus 1, which is the same as x squared minus 1, so those divide out. So we get 1 equals, here I get x plus 1, x minus 1, x plus 1, x minus 1, x plus 1 cancel out. I get a plus b times an x minus 1. Here I get an a times x plus 1. And I can distribute those out. I get an ax plus a. Well, there's actually two ways you can go from here. On the simple ones, there's a really nice slick strategy. Okay, but that doesn't always work. So I'm going to show you the method they show you in the book to equate coefficients. But then I'll come back and show you the way that's slick for some simpler situations. So bx minus 1, no, bx minus b. So distributed out those. And then I get, I am equating coefficient, I'm combining like terms. So I have an ax and a bx, so that's an a plus bx. And I also have a constant here and a constant here. So that's going to get me an a minus b. And on this side I've got a 1. So these are polynomials on both sides of the equation. There's a polynomial over here, there's a polynomial over there. And for two polynomials to be equal, the coefficients of each of their terms have to be equal. That's the theorem that we use here. So my coefficient for x over here is 0. My coefficient for x over here is a plus b. So 0 has to equal a plus b. My constant over here is a minus b. My constant over here is 1. So 1 has to equal a minus b. And then I get a system of equations, and then I can do substitution or elimination to solve. Yes?
Are you recording for
I am. I should be. Hold on. I thought I hit record. Yep. I just found out how to hide the bar. Because one day I accidentally turned it off with my hand when I hit the screen. So it was only the first 20 minutes of the lecture that got recorded. Thanks for checking. No, I appreciate that. All right. So in this, it's really nice. You can do elimination. You can just add those two together. You get 1 equals 2a. Your b's cancel out. And so a equals a half. And if a equals a half, then b has to equal a negative 1/2. Mainly from the top one, they add to 0. Okay? So that means that I can rewrite 1 over x squared minus 1 as one over 2, let me write it this way, 1 over 2 x, what was my a over, x minus 1? X minus 1 plus a minus 1 over 2 x plus 1. Okay? And in this particular case, you may recognize we actually did the integral of this problem yesterday. Or I guess Friday. So we did it with trig sub, but it's actually a little easier if you do partial fraction decomposition in this case. So if we're actually trying to find the antiderivatives of these, you can pull out a 1/2. You can, then I have to find out the natural log of x, the antiderivative of 1 over x minus 1 and x plus 1. And this you can do with u subs, but dx is going to equal du. So I'm just going to end up with 1 over u du, so that's going to be the natural log of x minus 1 minus the natural log of x plus 1 plus c. And 1/2 multiplied by all those. So there, that's the whole. That's a little bit easier than the trig sub problem. You avoid square roots this way. You end up with terms with square roots, which this is where the 1/2 comes in with the natural log. We could take those, use log rules and make some square root things out of those. All right. So the iClicker question asked what the sum of a plus b was, and if you add those together, you get 0. So the answer was C. Let's talk about another way you could solve for a and b. Let me pull up another page to talk about this. Once you get to here, this right side has to be, if this right side is equal to the left side, then the right side is equal to the left side for any value of x. So I can just pick and choose what x's I want to set up systems of equations. And if you're wise, you would pick x equals a minus 1 as one part, because then that would make your a's go to 0. So you would get 1 equals a times a minus 1 plus 1 plus b a minus 1 minus 1. And so that goes to 0. So you end up with 1 equals a minus 2b. So then b equals a minus 1/2. And then pick x equals, if you pick x equals 1, then this term will go to 0. And so you get 1 equals a times 1 plus 1 plus b 1 minus 1. And you just get 2a equals 1, so a equals a half. Works really nice when you've got linear factors and non-repeated linear factors. It's really nice. When you get into the irreducible quadratics, it's not as slick. So that's another strategy. I know Patrick JMT teaches that strategy. Okay. Questions so far? I'm going to talk about the general process and about setting them up, and I know there's some questions with that. But any questions so far with what we've done? Yes? If I select the value for x, what? Sorry? Oh, so like in this case where with x equals 1 and x equals a negative 1. So when I set up this partial fraction decomposition and I multiply through by the common denominator, I just get one equation here. That's when I do that. I can multiply out and combine like terms and equate coefficients to get a system of equations, or I can start just plugging in values for x. And if you're strategic in the way you plug in values, you can get a nicer system of equations, or get some terms to go through to some terms to go to 0. Did that answer your question? Okay. Yes. Okay, so the question was when you plug it back into the integral, or plug it back into, I didn't start off with an integral, but when we plug them back into here, oops, like for a and b, then that's right. I could have written it as 1/2 over x plus, I think it's x minus 1. X minus 1 plus a minus 1/2 over x plus 1. I could have written it that way, but then I would have, it's kind of ugly, and then I would have simplified it. So, okay. Another question? All right, let's do this problem. And I'm going to use this problem to just talk about the steps in general, okay? Okay, so the problem is to integrate that. Now just stop, think to yourself for 20 or 30 seconds, think about what would you do? Like with what you know about partial fraction decomposition, like how would you go about working on that problem? We are going to work through this, but think about what would you do and what are the troubles we're going to bump into. Now just think for a second. All right, so here's the 6 steps. Sometimes I put on 6b, which is don't forget about the long division part when you do the integration. Because if you do long division, you'll have some pieces that aren't rational expressions, and everyone forgets about those when you actually get to the integral part. But if you want to take a picture of this, this will be in your notes. But if for today you want to be referring to it, go ahead and pull out your phone, because I don't know if this will be on the screen the whole time. Okay, I'll be referring back to it, but just FYI. So we have a system for breaking apart crazy things like this if we first make sure that the degree of the numerator is less than the degree of the denominator. Can't be equal, it's got to be less than. That's what we're assuming when we set up a partial fraction decomposition. So in this case it's not, so we have to do long division, and most students in your shoes have forgotten how to do long division with polynomials, and I've heard they don't teach it as much anymore. So here's a quick review. So let's do long division. So x cubed plus 1 into x to the 5th plus 0x to the 4th plus 0x cubed plus 0x squared plus 4x minus 1. Okay? So I look at my first term here and my first term there, and I ask myself, I'm going to try this. It's not very big, but what can I multiply x cubed by to get x to the 5th? Okay. Okay, well, I tried. Maybe I can move that up a little bit. Okay, that's what I ask myself. What can I multiply x cubed by to get x to the 5th? What is it? X squared. So I'm going to write my x squared over there by my x squareds. And now I multiply x squared by the term that I'm dividing by. I get x to the 5th minus, n and x squared. And then I change my signs and add, or I subtract. The goal is I want to get rid of this first term. Okay, so I need to make sure whatever this is, it's the exact same value as this is. So when I change the sign and add, that goes to 0. And now I have 0, 0, 0. I end up with a minus x squared plus 4x minus 1. Now, this is a smaller degree than what I was dividing by, so I'm done. Okay? Because if I start to ask the same question again, what do I multiply x cubed by to get negative x squared? I have to multiply by 1 over x. So since this is smaller than the original number I'm dividing by. So I can rewrite x to the 5th plus 4x minus 1 over x cubed plus 1. I can rewrite that as x squared plus a minus x squared plus 4x minus 1 all over x cubed plus 1. So this is like this term right there is like my remainder. So I put it over my x cubed plus 1. And that's my first step about breaking this up. Already we can integrate a part of that, right? If we have to integrate x squared, we're good. But now this problem. How are we going to do this? We need to do partial fractions. What's the next step in doing partial fractions? Factor the denominator. How many of you know how to factor that denominator? If you do, you're a better man than I am or woman when I was here in your shoes. The very first semester I took 113. The semester I took 113 was the very first semester they gave a common departmental final. And they put some bears on there. Those some problems that were just horrible. And one of them was integrating by partial fractions where the denominator was the sum of cubes. And you had to know how to factor down the sum of cubes. And no one could remember how to factor down the sum of cubes except for like 5 people. And so we don't do that to you anymore. We still give you some problems, but they're a little bit more fair. Yes? Oh, good job. What is it? That's right. So this piece here is an irreducible quadratic. So that's as far as we go. So if you ever face the sum or difference of cubes, there's a similar similar form for the difference of cubes. It's x minus 1 x squared plus x plus 1, just FYI. But if you actually, all you have to remember is that for the sum of cubes, you get one of the factors is the cube root of the first and plus the cube root of the second term. And if you remember that much, then you can just do long division to figure out the other part, the long division that we just went over. So, and with the difference of cubes, you take the cube root of the first, cube root of the second, it's a difference, and then you can do long division where you just divide like x minus 1 into x cubed plus x cubed minus 1. But that's a side note, okay? So you don't have to memorize it as long as you remember the what that linear factor is in both cases. All right, so where are we in this big problem? We finally got that piece factored down. So this thing, is there a way for me to copy? I'm going to try this. That didn't work. Okay. Oh, how am I supposed to paste that thing there? Oh, beautiful. Ah, there we go. Thanks. Okay, so we know that we can rewrite that whole thing as x squared plus a minus x squared plus 4x minus 1 all over x plus 1 times x squared minus x plus 1. All right. Well, that helps us out a little because we have it factored down, and now we can take this side and just focus on the partial fraction decomposition. We won't forget about the x squared. So I can set up that. So you set up the partial fraction decomposition, okay, and compare with your neighbor. How would you set this up? How many terms would you have? What would you set up as your unknown coefficients? So go ahead. You can talk to your neighbor if you need. All right. So a lot of people do this. We cannot factor this down anymore. That's irreducible. Over the real numbers, you can factor down any cubic into a linear and a quadratic. But some of those quadratics over the real numbers we can't factor down. You can factor down anything over the complex numbers to linear factors. But we're not going there in this class. So, but now the question is, what do we put in the numerator? I saw a lot of these, but that is not correct. It's not just a over x plus 1 plus b over x squared minus x plus 1. Okay? We have to put a bx plus c over here. Okay? So you should have something set up like this. Now, you could, it doesn't matter what you call A or B or C. Some people that switched around, and so they may have had AX plus B over here and C over there because they put that x plus 1 term later. That's just fine. That doesn't matter. So, okay, let's talk about setting up. Okay, because I know a lot of you have questions about setting up and why we do this, the silly things that we do, or things that seem silly. I'm going to let's take a step away from this problem. Okay, and let's look at something kind of crazy. Now let's do that. All right, so here's a crazy thing. We can't integrate. Maybe we can break it down using partial fraction decomposition. And if we're always starting our rational functions with the numerator, the degree of the numerator is less than the degree of the denominator, then all of our terms, they can be, the numerator of each of our terms can be one less than the denominator. So one thing we could do here is we could start off like this. Dx plus. This is not what they tell you to do in the book, so I'm getting there. Okay. This is the furthest I think I've gone in the alphabet doing one of these things. We won't solve for these, don't worry. All right. So I actually could do that much. Okay? I have each of my three kinds of factors. I put them in the denominator, and I went 1 degree less. But we can simplify it further. And that's what we do. So you'll notice, like, already we could see how we can simplify this further, right? We could rewrite that as ax squared over x cubed, and bx over x cubed, and c over x cubed, and that is a over x plus b over x squared plus c over x cubed, and that should start looking familiar to you, because the book tried to teach you, hey, if you have repeated factors, you start listing out each of those factors up to the power that you have, and if they're linear factors, you just do constants. If they're irreducible quadratics, you have to have ax plus b over them. Okay? you can actually do the same thing with these. So according to the rule, we should be able to rewrite this thing as, we should be able to rewrite that as, instead of dx plus e, d over x minus 1 plus e over x minus 1 squared. And if you're a little clever, you can actually see it's not as easy as the first. It's not as easy as this case with x cubed, but if you take dx plus e over x minus 1 squared, and you're a little clever, you can simplify it to something that looks like that. And the clever thing that you do is I'm going to subtract a d and add a d. Depends on what your denominator is, but if I do that, then I get dx minus d plus e, and that's all over x minus 1 quantity squared. And I'm going to split it up, and where I'm going to split it up is right here. So I'm going to split it right here. So I'm going to get dx minus d over x minus 1 squared plus d plus e over x minus 1 quantity squared. And some of you may know where I'm heading with this, because now I can factor out a d from this term. And what did I just do? I can rewrite that whole thing as d over x minus 1 squared plus, this is just, this part here is just another constant. Oh, x minus 1, yep. Yep. Yeah, that's what we do with you guys on the test. I should do it to myself too. So. Right. But d plus e is just another constant. So I could just call that E, or really I should change it to probably like S or something. S looks too much like a 5. Q, there. X minus 1 squared. So we started with this thing up here, dx plus E over that, but we actually found we could actually write it as to just start off with something like this. Our D's and E's might not be the same as our D and our Q, but we can simplify it. And you have to be even a little more clever to simplify something like this with the irreducible quadratics. I'm not going to show you how to do that, but we can rewrite it as x squared plus 4 fx plus g and x squared plus 4 squared hx plus I. So even though we could just use the 1 degree less in the numerator rule and rewrite it like I did at the very beginning up here, it turns out we can even do better than that. And the way we're doing better allows us to break it up into even a lot more terms that are a lot simplified. Hopefully we can have a better chance of finding antiderivatives of those. Yes? So you might ask this similar question with like this term here, right? Why don't I have ex plus f, even though this is an x minus 1 quantity squared? This is really a quadratic term right here, right? Why don't I have ex plus f? That's exactly what I was trying to show, where I started off with that up here. And I can break that down even further, where I don't have, even though this is quadratic, this piece makes it so I don't have to worry about putting a quadratic in the numerator. And this piece here, similarly, this piece makes it so I don't have to worry about putting any higher powers in this term. So if you have an irreducible quadratic, doesn't matter how many powers of that irreducible quadratic, you're not going to have more than an ax plus b, than just a linear factor in the numerator. And if you've got linear factors, if you set it up with all possible linear factors, then you don't have to go any further than adding a constant in the numerator. Okay? Yeah. Thanks. Yeah, go ahead.
Where you put fx cubed plus dx squared, all that, did you mean to put plus hx plus I? And not plus ix?
Oh, I did. Yes. Thanks. Nice catch. I should have highlighted it. So, because it was my error. Okay, questions about the setups and why we set up the things that we do the way we do. You don't have to know why we set them up the way that we do, but a lot of students had that question after this, like, why do we do it that way? So I know a lot of you had. Some of you had asked me questions before even we came to class about why you do it that way. Okay, so let's go back. Where were we? We were trying to break this up. We have this set up, and we saw this is an irreducible quadratic over here, and so we need to have a bx plus c, and so now I can multiply through both sides by my my common denominator. So x plus 1, x squared minus x plus 1. Over here, x plus 1, x squared minus x plus 1. And let me delete these. And here, x plus 1, x squared minus x plus 1. Multiplying through by our common denominator allows us to get a much cleaner equation. So all of this will divide out with all of that. X plus 1 will divide out with x plus 1. I get ax squared minus x plus 1 plus bx plus c times x plus 1, because that term divides out with that term. And on this side, I end up with a minus x squared plus 4x minus 1. Yeah? Yep, yep. I'm just focusing on the ugly piece over here to get it into a couple simple pieces, and then I'll come back and do the integration. And I do not want to forget about that x squared. So, okay. Well, now what do? Let's multiply out and equate coefficients. You could this is a situation where it's not as slick to plug in x's. But so it's usually the examples in the book they give you, they're made so that when you equate coefficients you don't get anything too crazy. So what were you saying? Yeah. Oh, nice. Well, hey, maybe we should do it that way. So at x equals 0. Sorry, here, let's start at x equals a negative 1, because we do have one linear factor here. So let's make that 0 with x equals a minus 1. And so then you get, on this side, you get a minus 1 squared plus 4 times a minus 1 minus 1. And you get a 1 minus a minus 1 plus 1. This came from a minus 1 quantity squared. And that term goes to 0, so, oh, lib, how embarrassing. Oh. My wife even knows I'm teaching now. Why is she calling? Better turn that down. That's why I try not to even bring my phone to class. So. Got a PhD and I can't run my phone. All right, okay. So here you end up with a minus 1, minus 4, minus 1. So you end up with a minus 6. And over here you end up with the 1 plus 1 plus 1, so a equals 3. Yeah, so a times 3. So a equals a minus 2. But I don't think that's right. But we'll try it. Did I miss up? Yeah, over here if I plug in x equals a minus 1, then this whole term goes to 0. So, but okay. So then, if you let b equal 0, x equals 0. X equals 0, you get a minus 1. Here you get a, just a single a. B is 0, so you get just a plus a c. And in that case, what do you end up with? You already know that a is a negative 2. So a minus 1 equals a minus 2 plus c. So c equals, you add 2 to both sides, c equals 1. Okay. And then you've got to pick something else. Right? But if you let, already we can plug out in what a and c are if we want. But what did you get as your final? But, yeah. So you used x equals 1. So on the left-hand side, we're going to get a minus 1, a minus 1 squared plus 4. Oh, it's a minus 1. 4 times 1 minus 1 equals, here you're going to get a times a 1 plus b plus c times 2. Did I do that right? That, oh, that's a minus 1. Okay. So then this is a minus 1, this is a minus 1. Oops. So I end up with a minus. This is what I should just let you guys be solving this. So instead of you guys watching me solve this. 2 on that side. And here a I already know equals a minus 2, so this just is a minus 2. B or c is 1. So here I get 2b plus 2. And now I can solve, those add to 0, I get b equals 1. Okay? So, should look. So a equals a negative 2, b equals 1, c equals 1. Hey, that's actually what I had in my notes. Very nice. So, do you guys want to see the other way if we equate coefficients? Or no? All right, and everyone's like, no, this is enough pain. Yeah. So, okay, so this allows us, we have c equals 1 and a equals a minus 2. So now I can rewrite that whole integral as x squared plus a was over x plus 1. So plus 2 over x plus 1 plus and bx plus c. So then I get 1x plus 1 over x squared minus x plus 1 dx. All right, so that kind of looks like abscissa values. I'm going to pull that off. All right, so now we've taken that horrible, ugly thing and we've written it out as the sum of these things. This first one, easy. This one, u sub with x minus 1. This one, now, how do you do that? I thought I assigned a... We can't do partial fractions again because we can't break it down anymore. So, I thought I assigned a problem where you guys had to do this. Maybe it's still coming up. You have to complete the square here. The easiest way is to complete the square. And so, oops. and then do a trig sub or a u sub. So complete the square, then do a trig sub. You can also break it up. You can break it up into 2 right here and have x over that and 1 over that. On one of those you do, yeah, you still have to complete the square.
Alright, next time.
Yep, see ya.
Thank you.
Thanks, Brother Corey.
You're welcome.
Like in the summer. This is way too hot. But now